Okay, so let's make a start. So I want to talk today about this idea of threads in Java. So we had this idea the other week, that the other day, we had an idea that Swing used what we call multiple threads of execution. So we have the idea that when you start up a program, it starts at one of these threads, and then we said that there's this thing called the event handling thread, which runs in parallel with. Now, of course, on a whether that in parallel with is genuinely on a different core of the processor, or whether that's just simulated in software by swapping attention between the threads, doesn't matter. That's an implementation detail. But we said that there's this idea that these two things are happening concurrently, that from the point of view of the user, from the point of view of the programmer, you set a second thread going, and that keeps going whilst the remainder of the program is also going. So threads provide some kind of abstraction that allow us to talk about concurrency and things happening at the same time. So I want to talk a little bit about this in general today, this notion of threads. And this is a topic that's generally this topic about concurrency and processes that are happening at the same time is quite an interesting one, and there's a lot. You might do take this further if you're interested in this. It's an interesting topic to look into. So there's this basic concept that when you start a Java process, a Java program, you can have one or more threads running at the same time. So if you think when you start a program, it goes through a certain amount of time, and then multiple colours for different threads. This is what they call multimedia, I believe. So when you start your Java program, so you do main or whatever to start a program going, and then that starts a thread, and when the program comes to an end, it finishes. And during this execution of this program, you create various objects, which can have name, and then the state can change, and they can end, and create another object, and that ends at a certain point. And so you've got what we might call a memory space related to the program. We've got a group of objects and variable names associated with the program, primitive types and so on. So we've got quite a lot of information being created and destroyed during that program. Now, if I've got a piece of Java code, I compile it, and then I run it twice on the same machine. So if I open up two terminal windows on the machine, or I suppose it's possible to open up two instances of NetBeans. I don't quite know how this works so much in IDE, but I'm sure you can do this. You can run a program multiple times. So if I've got this program here, and I start it again, so I've got the same program, I've got a main, and I start it, and that will create an entirely different, what we'll call memory space. So if I run the same program, let's say it's a deterministic thing that just does a certain sequence of things, it will create the same objects at the same time, and there's no interaction between these two programs, at least not at this level. You might have a communication, deliberate communication through sockets or something like that, or some means of changing files. But if I create an object that's referred to by a particular name, like A, so I create a reference variable called A, and I assign an object to it, or I create a primitive type variable like an int, and I say B is equal to 27 here, and then if I create it differently, let's say, now that these are not so deterministic, let's say that that's a random number that's generated, and I generate the number 36 here, then those numbers are both called B, and they're both running within their own process. So if I start programs multiple times, each one has an address space, and they don't interact unless you deliberately make those interact. So it has its own memory associated with it. So that's the idea of normal Java processors. But this idea of threads is somewhat different. So what we have with threads is the idea that we've still got a main program, but within that main program you create a special kind of object that's called a thread, and you can do that in one or two different ways, which we'll talk about. So you've got some method that executes in this main process, and that starts another thread running. And what's different to running different programs or the same program on a system is that now the address space, the memory space, is shared. So if I create a variable name here, so if I now, let's extend this a little. Let's say, you've got these two variables A and B, and they exist for a certain amount of time. Now let's say B was initialized from this thread, so I put the value 27 in there, and then I've got something in this thread which says B becomes equal to 36. Then these things share a memory space. So the kind of program that's running here, the thread that's running here, and the thread that's running here can both access the same set of names. They can both access the same set of variables, the same instantiations of the objects. So you can obviously it's a bit more complicated that you have to deliberately pass the names between the different objects, but that's no different from passing names between objects in a normal thread, yeah? So that's basically the idea behind threads, is you've got one process that shares the same memory space, but these things run in parallel with each other. So you've got one thing happening here, one thing happening here. And then you could create another thread. So you could create another thread coming off here, or another one coming off from there, by calling the run method in that thread. And we'll talk about that in a moment. So as I say, the canonical example of this is graphical user interface. So you've got the main program, the main process running, the main thread, and then you've also got this event dispatching thread. So that runs along the same time as the main program, the main thread, and it basically sits around waiting for code that's initiated by one of these event listeners, one of these event handling procedures that we saw earlier. So that gives us the basic idea. We want to be able to do multiple things at once and pass information between those different things by shared names and so on. So why do we care about this? Well, we might want to, as I say, have a graphical user interface to remain responsive whilst the main program's doing something. We might want to have something happening in the background in a window So we might set off something that does a little animation or something in a window, and we put that in its own thread so that we can do stuff whilst that's running. So let's think about a simple example, some kind of video playing program. So that's animating a sequence of pictures on the screen, but we at the same time we want to be able to press a pause button or a rewind button. So you might think about those two things, the thing that controls the buttons, the controls for the video playing, and the thing that controls the playing of the video itself might naturally fit into two threads. Similarly, you might want to read or write a large file. So we talked about images. So we might want to do something in the background but still allow the user to interact with the program. So, we've got all these kind of things that might happen in the background. We might need to interrupt them, we might need to let them just take time. Reading and writing a large file, if you think about a web browser, you download a large book or a movie or something, and it pops up a little downloads window and displays a progress bar. And it doesn't stop. It doesn't say you can't browse the web for the next 5 minutes while that thing's downloading. That happens at the same time. So you've got your main web browsing thing happening here, and then that's a downloads thing which ends when the film's downloaded or something like that. So you've got this notion of things happening in the background, kind of. And other things, you might have something which takes several connections from different places. So, there's various ways of doing this. I think this first way is probably the definitive way. It's probably the best thing to do if you don't know what you're doing, don't have any reason to do it a different way. And that's something there's an interface built into Java called runnable. So remember how interfaces work? Interfaces basically specify the name and signature of a number of methods that must be implemented. And the method that must be implemented in runnable is an extremely generic thing. It's a single method called run, and its return type is void, so it doesn't return anything specific. And that basically is the thing that runs the thread. So when I start this thread, when I said I start this thread here, what I've done just before then at some point is to create some object which will be of a class that extends runnable, and then at this point that creates the thread, that's an execution in this red thread here of, so let's say we've created something called T, which is a thread, and then here I'll say, this is an object of some class that extends runnable, and then I say t.run there, and that basically starts that thread off. And from there on in, the remainder of the, unusually for things in Java, that doesn't sit there until it finishes. That just sets it going, and then it doesn't wait until that's happened. That transfers the control of that object to a separate thread, and then this program carries on running here, and then this thread carries on running as well. So that's the idea of this, and it's a bit more complicated than that, because you actually normally do this by creating for technical reasons. You create an instance of the thread class, and then you call the start method. So that was a bit oversimplified there. I didn't mean that, did I? Let's get rid of that. That's not quite how you do it. It's a bit more complicated than that. It's actually like this up on the slide. So you create that. I forgot about that. You actually need to use start there. but it's basically the same idea. So run is where you say what happens when the thread starts, and you actually do it by creating a thread that's got one of those runnable objects in it, and then you do start to start that thread there. So that's a very simple bit of framework for that. There's also now in the last few versions of Java, there's been something like executor service, which is a more complex thing, which you can look up if you get into this, which is a more sophisticated way of handling multiple threads and their starting and stopping them. So that's one way of doing it. This is the other way of doing it. There are reasons that you can look up if you're interested about why you might choose one or the other, and that's to extend thread itself and override the run method, and that basically behind the scenes is doing the same thing. Of course, the advantage of the first method is that when you've got an interface, you can do multiple things. Yeah, so you can both extend another class and implement an interface. So that's probably the best way to do it for that. But basically, you do the same. You do the same sort of thing. If you do that, you create an instance of that class called the start method. So here's an example. Class called foo. It extends thread. You, as always, you have a constructor that, in this case, just calls the constructor from the superclass, which is thread itself, and then you've got a run method which overrides the blank run method in thread itself, and then you create an object of that class, and then you say start. And in theory, you could do this multiple times. You could create multiple instances of the same thread. So if you've got, say, different animations running, you could create different thread objects in here. You could create a thread, you could create T1, T2, and so on, and then you could say T1.start, and so on, then T2.start, and that will create another thread, and you pass different pieces of information to it to animate different things. There's a little reference here which you can look up if you're interested, which is a discussion of these two methods and why you might choose one over the other. So is that basic idea clear so far?
It's probably worth pointing out you can call the run method, but if you do, Java will hang, obviously, because it replaces the current thread.
That's where I was getting.
Never call run.
That was where I was getting muddled up. Yeah, because I thought there was something odd going on there. I'd forgotten that you needed to do this. So obviously, run is accessible. It's a public method, but you need to create the start. Start is what has special behaviour that doesn't pause. It doesn't hang once you call start there. So you need to do this little bit of wrapping within a thread like that. So that's that. So there's lots of different issues here. So there's lots of different issues to do with concurrency and so on. And so we can have a think about this and how some of these are dealt with. So there's various issues to do with interactions between threads, which require some subtlety in how they're dealt with. I think the threading is very valuable, but it's also very problematic, and part of that's because you've got some notion of indeterminacy. Yeah? If you've got a Java program, that says do one thing, do another thing, do a third thing, do a fourth thing, and so on, then it's just happening. It's happening all within that process. It's well defined from the code which thing happens after another. Even if there's some kind of leap or some kind of randomness, you've got some notion of, during that particular run of the program, what happens, yeah? So you go through a sequence of states, and you can, particularly if you control things like randomness and user input, you can be sure of what's going to happen when you run the program multiple times. But let's say one of these things creates another thread. So you've now got another sequence of things happening. And what isn't specified particularly strongly, and what can change depending on what else is happening on the machine and so on, is how these things happen with regard to each other. So you might have all this stuff here, and then you ask a question like, let's call this thread 1 and thread 2, and you might ask a question like, does line D in thread 2, action D in thread 2, happen before or after action F in thread 1? And that's not well defined. That's not, once you start these threads going, all you're saying initially is that this is happening and this is happening, and they're happening more or less, at the same time. But there's no notion of going through them at the same rate in any sense. So whilst there is some attempt to balance the resources that are given to threads, it's possible that this could happen before this, or this could happen before this. So there's some, unless you do what we say on the, on some of the forthcoming slides, you can get this indeterminacy, and that can make these things very hard to understand if you get a problem, because you might get a problem that happens sometimes, but not others. So, what sort of problems do you have? Well, you have problems from this notion of a shared memory space. So you've got these shared names, these shared addresses, what we want to call them. Let's call them variable names. So you've got A and B there. They're objects or primitive variables within the shared memory for these two threads. And in theory, that's really great. You can pass information from one thread to the other just by changing the state of one of these shared variable names. Those are all shared variable names. But that's not always as simple as it sounds, because you might run into a problem about when something's been changed. So you've got this is the canonical example. You've got a simple command like n++, which adds 1 to the value of n, the variable primitive int or something like that. Now, what's happening behind the scenes there is a three-stage process. You get the value of n from the memory, you add it to the value, and then you write it back. So, if you're just doing this in a single threaded program, where you're going from one state to the next and you wait until an action's finished until you move on to the next one, that's not a problem at all. So let's say that's not happening. Let's say we've just got this program running here, and we say n++ there. The next thing that happens is not going to happen until that fetch, modify, return little cycle has happened. So we can be confident when we use this value of n down here that it's been modified properly. But let's imagine there are two threads. Let's imagine there are two threads that are accessing that. You might say, you might have the first thread. Oh, use this diagram here. You might have you can stretch this out and you can say this fetch, say this is coming from this thread here, fetch, change, and then write again. So you might say, and then you might try and do something with that value in a second thread here. So you've got n there, and then you might do this same sequence here, fetch, change, write from this other thread. So that's got a value, then the value is taken there, it's changed there, it's changed there, it's written there, it's written there. So, you know, what happens is rather than that happening twice, this one overwrites the change that's been made there, yeah? So rather than going fetch change right there, then fetch change right there, which is probably the behaviour you want, they've interfered with each other, and as a result, only one of those two changes has actually had an effect on the final value of the variable, because this right here that wrote the results of that change has been ignored by the fact that the value has been fetched for the second thread before that change has happened. So that's quite a subtle idea. So we've got the idea that somehow what we think is a simple thing, like increasing the value of a variable by 1, could actually, you could try and call that twice in 2 threads, and it might only happen once. And then when you run your program again, it might happen twice. You know, so this is this indeterminacy again. So depending on exactly when those 2 threads in the program executed with regard to each other. So there's a problem there. So this probably summarises it, yeah. So thread changes the variable and then another thread accesses the same variable. You know, it won't necessarily see the new value and so on. So, and there's particular issues with compile optimization and so on, which are a bit technical. I don't know that much about beyond that makes it even worse. And so we know that in a normal single-threaded program, if we've got some action A and some action B, we can be confident that A is finished before B starts. When you've got threads happening, they can interfere in odd ways. So one thing we can do is we can mark code as synchronized. So we can say we want to be confident that a particular piece of code is executed and let go of before another thread is allowed to modify it, any other thread. So basically we're saying that if we, and this would typically be something more, a larger scale than just a single statement. But let's say we say n++ there. I'll just do this in pseudocode and say, you know, sync n++. That's not quite the, it's a bit more sophisticated how you do it, but it's not much more. And then what happens is that says, that encapsulates all that whole set of processes there. So during this time here, that's all just happens. And then when you've got n++ here, rather than it trying to do it straight away as it did before, that thread will pause at that point and wait until that synchronization thing's stopped in the other thread. And so that will wait, that sort of waits there, and then when that synchronization, you know, let's say that's synchronized as well, when that synchronization's finished in the first thread, in the red thread, that will release it, and then the green thread can then do that fetch, change, right. That fetch, change, right cycle, yeah? So that gives us a very simple notion of being able to say for a particular thread, I want to reserve this little bit of activity just for that. So that's synchronization. So let's have a look at how this happens in code. So one standard way of doing this is at the level of methods, yeah? So methods are the basic atomic units of action in Java. So we might want to say that they're synchronized. So if we're using a method that changes a value of a variable that is shared between two threads, so n in this example, a method that changes that value, we might want to mark as synchronized, yeah? So we can do that. We can also, if methods are long and complicated, we might want to say that just a set of statements is synchronized. So, and it's not synchronized with regard to a specific thread, you know, a specific other thread. It's just a generic notion that if we say something's synchronized, we're grabbing it from the communal memory pool of all the objects that belong to that set of threads, to that particular execution of the program. We're grabbing it and holding on to it and preventing any other thread from getting hold of it. So here's an example of this. So a very simple example. We want to have a method here. We want to have a method here called increment and one called get count, and they both make it so that, you know, those happen. Those grab that variable called count and make sure that it's not being modified whilst that's happening. So that's that shows you how to use that keyword. You just put it before the method name. Quite too sure what could happen there. Could that go wrong in some way? Perhaps you could return it and change it in between it being got from the memory and being passed to the next use of it or something. But this one particularly has got an issue because of this fetch change right cycle there. So that's the idea of synchronization. So that's a very simple way of coordinating and making sure that you hold on to something. So what's happening here is basically what's called monitors or locks, which is that associated with each object is a thing called a lock, which is basically you could say it's a thing that refers to a thread. It's a name of a thread that owns that. So when a thread goes into some part of code that's marked as synchronized, some method that's marked as synchronize, it associates itself with the lock associated with that object. And then, so here, during this point, the lock associated with n is owned by this red thread. And then when it's finished, that lock passes over to the green thread. So we've got that notion, you know, only one thread can only give a lock. So, like I say, if you try and do something that's already being used, that's synchronized there, then it just stops. It just waits until that's finished, and then it takes that object to do something with. So that's the core idea in this notion of threads, is this idea of locks and monitors and synchronization. As I said, you can do this at the lower level, so you can put synchronized before a set of statements, and there you do need to specify a specific object. Almost always that will be the thing that's currently owning the things that are within it, but there may be situations where it's sensible to synchronise a set of statements with regard to another thread, but that's actually, I can't think of anything off the top of my head where that would make sense, but there's presumably reasons for it. So that's the notion of synchronising code. Synchronising a method would be the typical way of doing it, but there is this notion that you could make a little block of code and then synchronise just that little block, that little block of statements like that. So that's the idea of shared variables between threads. So, oops, that wasn't meant to go to there. 10 slides for it to there. So, there are a few things that are safe from these sort of problems, and we call these atomic actions. So these are things that just happen, and this isn't particularly something that's defined in the. This is typically something that happens because the activity is so small that it doesn't. There's no the underlying process in the Java virtual machine is just a single. It's just a single command. So these are ideas of reads and writes for object references and so on. But there is also a notion of a keyword called volatile. So you can mark things with this, and that's another way of making it so that access to those things happens as a single action and doesn't get interfered with in between those things. So you can mark variables as volatile as a way of avoiding some of those problems. And particularly this works by changing some of the things in the Java compiler. So when Java gets compiled, there's a straightforward notion of compilation that this changes the Java code into Java virtual machine code, and then there's a more sophisticated notion of compilation, which is that the code that's generated optimizes access to variables. So if you've got a variable name somewhere in your code, you make a change to it and then access it another bit further down the code, then the compiler might reorganize things so that change happens later. It might say, well, that's not used until then, so let's not change it until later. So these compiler optimizations can reorganize the order in which things happen within the compiler itself. So this prevents that happening. So it's good for coordination, but you wouldn't want to make that a default. You wouldn't want to make every variable like that, because these compiler optimizations can be a good way of getting code to run faster, to prevent things happening multiple times, and so on. So there's that notion of volatile variables, marking things as volatile. That doesn't mean that they become volatile. It means the reason for the choice of the word is, I presume, that it means that you're not saying this is becoming more volatile. You're saying the compiler should be aware that this is volatile. So it's a slightly strange use of a word compared to the other things you put before a variable name in Java. So when you start to get multiple things that are reserving reserving multiple variable names, you can get these sort of problems where there are threads which are trying to access the same resource. So you get this this process called deadlock. So if you've got two threads, and that thread's trying to access something which is currently locked by that one, and the other, and vice versa. So the red thread is trying to access some resource that's currently locked by the green one, and the green one's trying to get something that's accessed by the red one. You can get a problem there. So there are more sophisticated ways of dealing with this, and you know, this is a big problem. This is a big problem for concurrent programs. There are also things like starvation, where a thread is taking up all the resources and not giving much time for the other thread to execute. And there's more of a more sophisticated and rare thing, which is called live lock, which is where two threads, whilst they're releasing resources, they're also taking something else that's needed by a thread. So this is the best analogy I heard for this was like this situation where you're walking down a corridor and someone else is there, and you move to get out of the way, and the other person does that as well, and then you move back, and so you can imagine that happening as information gets passed. You know, you're both trying to access from a common pool of information, and so this thread, you write some code there that releases that information, but that's also then, you know, some other information is released by this, but then that grabs some information from there, and so there's this kind of swapping around, and you never actually have all the information you need to carry on with the process that you're doing. It's always locked by some other thread, even though you're trying hard to pass the information between the threads. So there's a lot of things to think about if you do more sophisticated threaded programming. This probably doesn't happen when you've only got a couple of threads going, because if you've got a very heavily threaded program, these become big problems, and at that point you need a more sophisticated approach to concurrency that takes these things into account. So let's think about communication between threads. So in the diagram I've got here, these threads just go on forever. Yeah, they just carry on. But you might want one of these things to go only for a certain amount of time. So you might want the notion that you've got some kind of main program that's running. It launches a thread to do something. So let's say let's take the definitive example, which is video playback. So that's playing back a video. And the things that happen in the main thread, you've got a play button that starts the video playing, but then you've also got a stop button. And what you want there is, when you do the stop button, you want to send some kind of signal to this other thread to say stop, and stop the video playing, and at that point the thread, you want the thread to stop. So how are we going to communicate between these threads? Well, there's various ways of doing this, and there's something called interrupt method, and then that interacts with certain other kinds of methods, sleep and wait. That's a bit of a technicality there. But let's have a look at how we might do this in, sorry, let me just, so there's something called interrupt that can basically grab the attention of the thread. I'll come back to that in a moment. There's some other things to talk about first. One thing you can do is to delay a thread. So you can have this thing called sleep, and that gives a certain delay to it. So you might want to pause the thread from happening, and so you've got that notion of sleep, so you can pass information between threads in that way. So you can say, I don't want this to happen for a while, I want it to just stop executing for a while. But we might think a bit more in a more sophisticated way about how to tell threads to stop or pause. So threads do have methods called stop, suspend and resume. But that's they've been problematic because they don't release the locks that are owned by that thread. So they're on their way out in Java. You might see them in some older code. And again, there's a way that, I don't know whether this is good or not. I mean, this illustrates how we're not at a very advanced stage with this kind of programming yet, certainly not in Java, which is that one way to do this is to set some kind of variable that's then monitored regularly from inside that thread. I don't like this as a solution either very much, but it gives you some way of doing it. So you've got some shared variable, and you say if you want the thread to pause, you set that flag. You might call it pause, and you set in this thread, and then you change it from that thread there. So pausing video is a really classic example. Yeah, you've got a pause button there that makes that thread pause until you press the play button again when it resumes, and then you've got a stop button which stops that thread that's playing that video and tidies up, closes the window, and so on. So one way to do that, as I say, is to set a variable. So you might have a variable called pause and stop within that thread. But the burden for that, and the fact that the way in which this seems very crass, is then that you need to constantly be looking at that variable and saying, should I stop now? Should I stop now? Should I pause now? Should I stop now? And that seems an awful burden of resources if this gets more complicated. That seems an awful lot for that thread to be doing all the time. So here's the details of the code for that. So you might have some kind of loop or something which does that if you just want to wait for something. But that's not really going to be how you want to do it. That's going to take a lot of resources because it's constantly checking that variable. So there is a way of doing it using a method called wait. So here's some code for that. So you've got a variable called paused, which starts as false, but then you can pass a change to that there, and if it's paused, you just wait until it's changed. And similarly, think of similar code to stop a thread. So the wait suspends the thread until you've got this particular notify method or an interrupt occurs. And again, there's sophistications to do with locks and so on. So you need to think again carefully about who owns, which thread owns what information. And then there are these methods called notify and notify all, which allow you to start these threads again. So that's that. So let's summarise it all. So we talked about this notion of threads, this notion of having multiple concurrent activities going on at the same time within the same program. There's communication using shared variables. But that's complicated because shared variables open up these problems of memory synchronization and so on. So there are ways to do this using synchronized code and volatile variables. And then we've talked a bit about potential problems with this stuff to do with deadlock and resource starvation and live lock and those sort of problems. They shouldn't be a problem for simple programs in Java, but they do become a problem when it gets much more complicated. And then we've talked about how we can communicate between threads and stop and suspend threads and use interrupts and notifications and waits and so on to stop and suspend threads. So that's that for today. On Tuesday, one or two of you were asking yesterday about whether there's going to be a lecture on Tuesday, which is blank in the timetable on the middle page. There will be a lecture on Tuesday. What it's going to be about, I'm not too sure, but Richard said he was going to do something on Tuesday, so he's going to do something there, but he didn't tell me what it was. So yeah, okay. So see you next week. Okay. Thank you. If anyone hasn't signed the attendance sheet, it's there. Hi.
Imagine we have a low priority thread currently executing.
Yeah.
And a high priority thread comes along and it releases the processor slot.
Yeah.
How do you know where you left when you call the notify to tell you the execution start?
The thread knows where it was. The thread starts from where it.
It will still be on the stack.
Yeah.
It will be on the stack. But
therefore, it knows exactly where
it is. Yeah.
Okay.
So once the other thread pops itself off, then
It
knows
doesn't
where you were.
delete any information to do with the.
Doesn't it have a program?